I wanted to cover this schematic diagram that shows up in the homework assignment for homework number 2. All right, so specifically, I think you're going to have some heartburn over this AND gate, or these series of AND gates that look like they only have one input. All right, well, there's not just one input. This is a shorthand notation for a more complicated underlying structure that hopefully we'll get into a little bit more towards the end of the course. But I wanted to explain the setup. All right, so first of all, in this setup, we have what we call double rail inputs coming into all of this, into this whole array of AND gates. All right, double rail just means that for a given variable A, you have both the variable A and a bar available. So we see with this line, here is A, and then we can also have, at the other side of the inverter, this would be a bar. All right, so double rail inputs. All right, so when you make a connection here, and we indicate connections with dots, basically. Okay, so when I make a connection, let's say I connect this point and this point. All right, then what that would really mean is I have a whole bunch of lines coming into this AND gate. All right, one of them would be B, and that's actually connected into the array. If there's no connection, it doesn't serve as an input. That's one way to think of it logically. Okay, so in this picture here, this gold symbol, gold AND gate here, actually has lots of connections, but it would be very messy and very sort of clouding the issue if we showed all those connections going into that AND gate. All right, so in this particular case, what I've got is an output where I have the variable B connected and I have the variable C bar connected. Nothing else is connected, so nothing else would come to the gate. So this would be B C bar. All right, so I can make some other connections. If I did this, okay, I would have coming to this second gate A, B bar, and D bar. All right, so hopefully that gives you an idea. I think that it's pretty straightforward. If you are given the connection points in this schematic, you can write down the output. This gate array is used to implement a sum of products formulation within this structure. Okay, I also wanted to go the other way with that and talk about how you would implement, in this example, I wanted to implement a product of sums type of Boolean expression. All right, so whenever you're looking at a truth table, basically you can indicate where the logic function f should be a 0. All right, so if f is a 0, f bar is equal to a 1. So I'm going to start with f bar and make this product of sums formulation that looks like this. All right, so keep in mind this is f bar. All right, so the reason I do that is I wanted to apply a complement. So if f bar indicates where the zeros are, so when f is a 0, f bar is a 1, if I do a complement of f bar, okay, f bar bar would be back to f. All right, so now I take the whole logic expression and I put the complement sign over everything. All right, so from there, I'm doing De Morgan's theorem on each piece. Okay, so the De Morgan's theorem would be I break the line, break up the complements, and all the and symbols in between. All right, so I'm going to draw those dots in for the and symbols. They turn to ors. All right, so let me highlight those. These green ands turned into ors, and I broke the line into pieces. All right. And so then the next step is to do the same thing. So I'm going to kill off the golds here. Do the same thing for these pieces. All right, so I'll start with a different color. I want to change that, okay? So I take each of the signs and I convert those to ands, and each of the variables get a complement. All right, so I started with A bar, it becomes A bar bar. I start with B, it becomes B bar. Start with C, it becomes C bar. All right, so I applied De Morgan's theorem for that piece. Okay, so you continue on and do that for the other three expressions. And so finally, whenever I see a double bar becomes just A, all right? And we end up with a final expression F that looks like the following. All right, from there, I can implement that into the schematic. All right, so let me grab this so that we can get it close by. All right, so I'm going to take this, move this up here. Okay. All right, so now what I do is I want to implement A, so I program that connection at A. B bar, make the connection at B bar. C, make the connection at C. All right, so for the next expression, I need to go to a different AND gate, all right, because it's connected through the OR array, and so you see this symbol comes into that OR input. All right, so going to the next gate, A bar gets this, I missed the line here, so you gotta be careful. That should have been here. So A bar gets this connection, all right, then B, and then C bar. All right, so that gives me this term. All right, just for completeness, let's make that red. All right, and then the last term, we can go with maybe purple. All right, so we have B bar, C bar, and D. That's this expression. So it ends up being a sum of products. So we converted a Boolean expression for the zeros in the truth table using De Morgan's from a product of sums to a sum of products, and we get an equivalent realization of the logic function F. Okay, so hopefully this will help with the homework and help you understand this sort of unusual drawing that shows a gate array for sum of products.